Today we will discuss about physical media. Hope you can hear me. Hear me as well as see the slides. Someone can respond by audio.
Yes, sir.
Yeah. Okay. Fine. So we'll discuss about the physical layer. So say when we discuss the network layers, we will see that the lowermost layer is a physical layer. Basically, that is what connects the different entities in the network, the physical layer. You can have physical layer as either guided media or unguided media. Two ways you will say that. Guided media and unguided media. So you have the center and there is a receiver and there is a transmission medium. Guided media, you will say the cables, all those things are guided media. Waveguides, if you are started with the microwave lab, you will say waveguides. Waveguide, your microwave communication, your cell phone communication, all those things, they proceed in the using waveguides. So say electromagnetic waves are conveyed through hollow pipes. Reflections, so T, TM, all those reflections you will come across that. So Smidhamas is engaging that. So you will learn about microwave communication, and you have a lab also. Again, unguided media is the free space. You have different ways to say Wi-Fi, Bluetooth or satellite, all those things. These are unguided media, you can say. Guided media, there is one more thing, optic fiber. Fiber optics. Fiber optics is another guided media. Coaxial cable is guided media. So we'll see that. So this is this is the classification. You have the transmission media classified as guided as well as unguided, and you have twisted pair, coaxial cable, fiber optic cables, and the unguided part you have the free space. We have different. We'll see the different components of this of each of these. So this is the twisted pair cables. It's credited to invented by Graham Bell himself, Alexander Graham Bell. So so you have two wires which are twisted together. So you have some degree of electromagnetic shielding. You have crosstalk issues will be still there. So then there are two types of twisted cables, you can say. This is unshielded and shielded, that is STP and UTP. On cables you will find that. So the STP cables will have a sheath across this, that is the shielding, and it is having better noise immunity, less interference from other sources. It's costlier, although it is having all those features. It is costlier. This UTP cables are much cheaper option. Okay, so so STP and UTP cables are there. Then you say this is something which is ultimately your physical interface to the what do you say, the network. Say if it is a wired network, it is the RJ45 Jack. RJ14 is there. Telephone cables, RJ14. RJ is standing for registered jack. We have seen this sort of connectors. You say what do you say, LAN connector. The actual thing is RJ45. It's called as RJ45. For different types of networks of different speeds, there are different categories. Usually Cat 6 Cat 6 is usually there. Cat 5e or Cat 6, that is what in usual places we put. Category 6, so that is, it's an unshielded one. It's an unshielded one, UTPN. Then there is coaxial cable. Coaxial cable is say you would have come across this usually this what do you say, something which is used in your cable TV, that is RG59 cable TV connector. It will have a if you have seen it, you will have a what do you say, wire mesh like thing outside, which is a shield, then a copper cable in the center, and a plastic what do you say, or a dielectric insulation in between. So So this is the RJ59 cable TV. RJ6 is also used, thinner ones. So then Ethernet, earlier days of Ethernet is you could say it is it's a local area network thing. So Ethernet or the LAN, they are used interchangeably, and they have a characteristic impedance. You are aware of the maximum power transfer theory. The load impedance and the source impedance should match. So this is for impedance matching purposes. In your electromagnetic theory, you will come across certain other things also. So characteristic impedance. Then this connector, you are familiar. What sort of connector is this? The CRO probe connector, you will say. That is, it is technically called as a BNC, bayonet nailman concealment connector. So this is a invention from the World War II times. So it's say it has a lock which fits into the device, locks there. They use this thing first in ships, naval ships, so that it will the equipment used there, it's subject to rough seas and all, so constant shaking, all those things are there, so that it won't get detached. So it's a bayonet. Bayonet is something which bayonet charge, you could have heard about that. The police or especially the army people, they train with the knife like thing in front of their rifles, and they charge. That's called as a bayonet. So it's a bayonet nailman concealment connector. So this is having very less loss, but at higher frequencies this will be an issue. Say for microwave frequencies, you have a different type of threaded type of connectors. This is not a threaded one, this is a lock-in one, lock-in place. So that is a coaxial cable. These are all guided media. Then fiber optic communication. This is say the future. It seems we have a lot of surplus fiber capacity installed under the National Optic Fiber network. Even in our campus, you have that orange cable which is not dug into the ground, rather it is hung over it, connecting various departments. So even one strand can carry several megabits of data. So for each fiber which is laid, you have a redundant capacity. So when you walk across the road, alongside you will find pillars which indicate the path of optic fiber. So telephone exchanges, mobile base station, mobile towers to their BTS stations, all those things are interconnected by fiber networks or optic fiber cables. So this is one of the fastest form of communication which we have as of now. So that's why we are having a real-time class, almost a near real-time class as of now. So fiber communication is making it possible, and it's based on a very simple thing, which is Snells Law. Snells Law has to do with the interface between two media, that is, which has two different refractive index. When a ray of light, you have learned it, that is, ray of light travels from a rarer medium into a denser medium, it bends towards the normal. It bends towards the normal. So it's shown the other case. So it's traveling from a denser medium to a rarer medium, bends away from the normal, and you have a relationship between the angle of incidence and the angle of refraction. So this is the relation, and so this has to do with this total internal reflection. That is why the light is conveyed through the fiber. That is, when this angle exceeds the angle of incidence exceeds the critical angle for the pair of media, the most part of the light will be reflected back to the denser medium itself, the first medium itself. That is the principle on which the optic fibers operate. You have a core and a cladding. You are aware of this from your physics classes or your +2 classes as well. So you will learn optical communication. I think this semester there is optical communication. So the fiber, optic fiber, has a core and a cladding. We will see in the subsequent slides. Core and a cladding, and the light is conveyed through the fiber. So there is loss also. So when the light travels through the fiber, on top of the fiber, that is outside the cladding, inner is the core through which the light travels, there will be some leakage obviously to the outside, and also there will be a small electromagnetic field which is traveling on top of these fiber, you can say, at a short distance from the cladding, from the core. So that is what we call as an evanescent wave. You will learn about evanescent waves in your fiber optics classes or the labs. So evanescent waves have different uses. Fiber optics are used for as sensors, biosensors and all such things. So this light gives us a lot of possibilities. So this is total internal reflection, the phenomena which you can see in nature. The swimmer in a swimming pool or a tortoise. So this is total internal reflection in action. Now this is a thing which is this has been put here simply for just to, this is a rain sensor. So rain sensor in automobiles, there is no other thing, other principle involved in this other than total internal reflection. You have a light source and what do you say, a photodiode combination here. So the light is being this interface has a particular critical angle, and what happens is that when there is raindrops, the intensity of light that is received at the photodiode varies. So that's how you perceive this rain, and then you deploy the wiper automatically. So there is a very simple physics involved in this, but they charge a huge price for this particular gadget. So you can add in as accessories, but I would prefer to turn on the wiper manually, because I can see and turn it on. Why to over rely on technology? That is one thing. Whatever technology is there is for our comfort, but if we are relying too much on technology, ultimately we will become very lazy. Okay, so that's there. This is how your an illustration of how the light travels in a fiber. So you will call them as different modes, the propagation modes, you can say. You see the wavelength, it varies depending upon how the angle of this light source is varied. So this is a GIF file actually. So usually if I am assigned to the optic communication lab, I usually have this demo along with other things. So this is lifted out from those slides. That's there. Then there is different types of connectors. Those of you who have what do you say, fiber optic networks in their homes, you would have using this SC type of connectors. SC type of, that is subscription channel connector, that is what. Then this you will find in our labs, fiber optic labs. ST type, FC type illa ivda, ST type ullathu, threaded illa. So ferrule type illa, this is there. ST type connectors there in our optical communication lab. If you are aware, we have an optical communication lab just next door to the network operating center, the HOD's floor there. So ST type is there, straight tip connector is there. This is actually a transparent thing, and there is a small glass window here. So inside this black thing there is optic fiber, and it is and the fiber is terminated at this point, and the light travels through this, and you can connect to the equipment. The light will given to the, so it's different devices are there, to measurement equipments are there. I know to connect them. So that is how light is coupled. Now we mentioned about the fact that in our campus the CCF, the central computing facility, is connected to various departments via this fiber optic cable. So at the network center there, in our department, there is a, if you have been there and inside the NOC, when you are in the campus again, you ask Lalu sir's permission. Lalu sir is in charge of the NOC here on department. So here there is a board where you are terminating the optical link, and then you convert those optical signals to electrical signals, and then you give to the LAN. So the LAN cables from another rack. So there is an equipment which converts this optical signals to electrical signals. That's the same thing which happens in your fiber optic router or PON devices, which you might, if you have a fiber to home connection, so you can take a LAN out from that. So optical to electrical conversion is also happening, electrical signal conversion is also happening. So this is regarding the fiber optic connectors. So there are two modes, say single mode and multi-mode fibers, those all things. So we mentioned about the core cladding. This is just for the sake of completeness I have included here. This particular guy, Dr. Narendra Singh Company, he is actually the one who invented this optical fiber. This guy this is not from any movie, this is the actual person. He was doing his research in UK, and here he is there in this picture. So, and he made the first fiber optics. He is an Indian, and he made the first fiber optic cable as part of his PhD work. He was educated in India. He went abroad to study in UK to do his masters as well as thesis and PhD, and he made this fiber, and that was commercialized later on. But he is the pioneer. He is a pioneer regarding this. He is a very good entrepreneur also. He is now in US. I think he is a US citizen as of now. That's what my understanding. You can Google for this person, Narendra Singh Company. So he is he missed the Nobel Prize due to various reasons. He should have been awarded the Nobel Prize, but at some points, due to various reasons, he missed the bus. So, but still, no one can deny that he is the one who is the pioneer. Then, unguided media, you have the electromagnetic spectrum. Different portions of the electromagnetic spectrum. You have the we have very limited portion of the spectrum available for communication. We are not using X-rays, gamma rays, all those things or cosmic rays for communication as of now. Maybe in future we might use even X-rays for communication. I don't know, but it's possible. Our range of communication available portion of the spectrum we are using for communication is very limited. We are using the visible spectrum. Yes, you and me use this visible spectrum portion of the communication. Ultraviolet, UV is also used to some extent. Microwaves, yes, our lot of communication happens in this microwaves portion of the spectrum. Radio waves, AM, FM stations, all those things. See, here you have the CDM, GSM, CDM services. What is GSM, CDM, and all those things you will learn. Then coaxial cable, all those things. Then here the earlier old systems, they work in this domain at higher wavelengths. The wavelength is decreasing. Here it is increasing. Here it's at this is lower frequencies. This is higher frequencies, higher band. So we use laser communication also. Last day there was a laser is also used for communication. Inter-satellite communication is via lasers, it seems. So it's possible. Then there is the classification of these bands, unguided media. Different purposes. There is a broad classification as to what is the range of frequencies. Say very low frequencies, medium frequencies, high frequencies. Say your FM, all those things then come in the VHF band. that is 88 to 108 megahertz. All the commercial FM stations operate in this band, 88 to 108 megahertz. So if you tune into any of these FM stations in your city, you will see that it is 92.8, 92.1, 101.4. Close by frequencies are there. You would have learned in your communication engineering paper this radio capture like things. Okay, then how the guard band, all those things are coming in there. On the other hand, you have the AM station which operate in the kilohertz range, that is 540 to 1650 kilohertz. So that is in the medium frequency. Then still you have what is the short wave. Short wave is use MW, that is the radio Voice of America, Radio Ceylon, or the All India Radio International band. All those things, they operate in short wave region. So here there is the other one, the cell phone devices, all those things, the higher UHF band. So you have this all the GSM, all those devices, 8 megahertz, that band, 8 megahertz band. Then you have the CDMA operating at much lower bands. Then satellite communication, 812 gigahertz, that is what 812 gigahertz are a common band. So navigation purposes, you have these things. So there, even in this all these bands, there are a lot of restrictions in a lot of band uses. That is, a lot of things are kept aside for classified frequencies are there, military frequencies, all those things you cannot operate. But the problem as of now is that the available bandwidth is limited, whereas the need for bandwidth is tremendous, the demand for bandwidth is tremendous. That is the reality as of now. So we have to make optimum use of the available bandwidth. That is the thing, and we are trying to use have clever techniques to add in more channels in the available bandwidth, multiplex channels, then shared channel usage, all those things you will come across. So again, that's winding up our discussion about the physical media.